Geometry in Algebra 2, seeing how we can apply these ideas of trigonometry to right triangles. Okay? So as you can see here, we've got a right triangle drawn. We always have to have what we call a reference angle, a point of reference. Where are we starting from? Okay? And that's our theta. Okay? And notice the triangle is labeled. We've got the hypotenuse is always the side that's opposite the right angle. We've got the side opposite theta, and we've got the side adjacent to theta. Opposite being across, and adjacent being right next to it. Okay? And you can see that using the lengths of the sides of the triangle, we'll be able to define the 6 trig ratios that we had in the unit circle, but apply them more to just the triangle. And since all of the angles in the triangle are going to be between 0 and 90 degrees, all of these trig functions are going to have positive values. So, here's how all these trig functions are defined when we apply them to the idea of a right triangle. The sine of theta is the ratio of the opposite side, or the opposite leg, over the hypotenuse. The cosine is the adjacent leg over the hypotenuse, and tangent is the opposite leg over the adjacent leg. And again, we don't have to memorize the cosecant, secant, and cotangent because they're still the reciprocals. The cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine, and the cotangent is still the reciprocal of the tangent. So it's really just important that we know the first three, the sine, cosine, tangent, and then remembering that the other 3 trig functions are all simply just the reciprocals of those first 3. So here we're going to look at a couple examples, and it wants us to find the exact values of the 6 trig functions of theta, which means it's either got to be a fraction or some integer, some rational number. We don't want any type of a decimal that we've had to round off. If it comes out to be a radical, then we'll leave it as a radical. But we don't want to have to do any rounding because we want the exact value. So, if we start here in problem number 1, and we look for the sine of theta. The sine is the ratio of the opposite side over, or divided by, the hypotenuse. So the sine of theta is 3/5. That's it. That's an exact value. Okay? I don't have to do anything more to it. The cosine of theta is the ratio of the adjacent side, or the adjacent leg, with the hypotenuse. So that's 4/5. The tangent of theta, we said, was the opposite leg over the adjacent leg, 3/4. What about the cosecant of theta? Well, the cosecant is simply the reciprocal of the sine. So if the sine of theta was 3/5, then the cosecant of theta will be 5/3. Cosine of theta was 4/5. The secant is simply the reciprocal of the cosine. So the secant of theta is 5/4. And the cotangent of theta is the reciprocal of the tangent, which gives us cotangent of theta 4/3. Okay. So those are exact values. I just left them as fractions. I just write the ratio and I'm done. Okay. The only thing I have to worry about is if there's any radicals involved, and I might have to rationalize if my radical ends up in the denominator. So if we look at problem number 2, you can see in this case we only have 2 sides of the triangle. We're going to need the hypotenuse. So in order to find that hypotenuse, we have to think back to the Pythagorean theorem. Okay. So we're going to use the Pythagorean theorem to find the hypotenuse of the triangle. So if we apply the Pythagorean theorem, we have 8 squared plus 15 squared equals, and I'll just call it c squared. And if we solve that, we're going to get 17. So now that we've got our 3 sides, now we can look at our 6 trig values. So the sine of theta. Sine is opposite over hypotenuse. But now, see, my theta is the upper angle, so the opposite leg is 15. The hypotenuse is 17. Cosine of theta is the adjacent leg, which is 8, compared to the hypotenuse, which is 17. And tangent of theta is the opposite leg, which is 15, divided by the adjacent leg, which is 8. And again, those are the 3 important ones to know Because then all I have to do to get cosecant is, remember, it's the reciprocal of the sine. So that's 17/15. The secant is simply the reciprocal of the cosine, 17/8. And the cotangent of theta is 8/15. It's the reciprocal of the tangent. Okay? So I'm pretty confident that this is all just review from geometry and algebra 2, just giving you these examples as a little bit of a refresher. Okay, moving on. Okay. Find the exact values of the sine, cosine, and tangent of 45 degrees. Okay. Well, if you notice the triangle, we don't have any values, so let's just throw a value up there. Let's say that this side here is 3. Being a 45, 45, 90 triangle, we looked at these examples the other day. Remember, since it's 45, 45, the two legs are going to be congruent, which means this side is 3. And by either applying the Pythagorean theorem or the special properties of a 45, 45, we can get the hypotenuse to be 3 square root of 2. So now let's look at these. If I look at the sine of 45 degrees, remember sine is opposite over hypotenuse. But if I simplify this, that's going to simplify to 1 over square root of 2. And when I rationalize, I get square root of 2 divided by 2. The same value that we had in the table. Okay? So even though if we thought of this triangle as being, and our hypotenuse here as being a radius, even though it's not the unit circle radius of 1, the sine of 45 is the sine of 45. It doesn't matter how big or how small the triangle is that it's a part of. As long as there's a 45-degree angle, the sine is always going to be the same. And consequently, so will everything else. So if I did the cosine of 45, I'd have the same thing. Adjacent over hypotenuse simplifies to 1 divided by square root of 2, which simplifies to square root of 2 over 2. So what do you think that means about tangent of 45 degrees? Well, if we remember the tangent of 45 degrees is the same as tangent of pi over 4 from our unit circle, that's always going to simplify to 1. Opposite leg is 3, adjacent leg is 3, 3 divided by 3 is 1. Okay? So it doesn't make any difference how big or how small my triangle is. If it's got a 45-degree angle in it, okay, if it's a 45, 45 right, the sine, cosine, and tangent are always going to simplify down to those same values that we have in our table. Okay? The same thing's going to hold up for the 30. Okay? It doesn't matter. Let's say I make the hypotenuse here 4. Well, we said the other day in a 30-60 that if the hypotenuse is 4, then the short leg is going to be half of that, so that's 2. And the long leg, which is opposite the 60, is the short leg times the square root of 3. Well, now if we apply our right triangle trig, the sine of 30 degrees would be the opposite side over the hypotenuse. That's 2/4, which simplifies to 1/2. Same thing that was in our table. Okay? Cosine of 30 degrees is the adjacent leg over the hypotenuse, which simplifies to square root of 3 over 2. Same value that we had in our table when we did our unit circle. So, tangent of 30 degrees is opposite over adjacent, which simplifies to 1 divided by square root of 3, which rationalizes to square root of 3 divided by 3. The exact same sine, cosine, and tangent values that we had in our table. So again, the sine, cosine, the trig values are unique for every angle. They're not going to vary no matter what the application is, no matter what type of triangle I've got. If I've got a 30-degree angle, the sine of 30 degrees is always 1/2. It doesn't matter how far out those sides are going. Okay? So those values are always going to be unique. Now, we have this idea of what are called cofunctions of complementary angles. Okay? And if you've kind of been looking at your table, you might have been noticing some of those things. Okay? When we talk about cofunctions, if theta is an acute angle, okay? Remember, 90 minus theta would represent the complement of my angle theta, because we're saying that theta plus some other angle would give us 90. So, if I know theta, remember I find the other angle by subtracting from 90. So, if I've got the sine of 90 minus theta, remember the 90 minus theta is representing the complement, then its cofunction is cosine theta. So for example, if you think about it, if you look at your table, and you look at the sine of 30 degrees, or the sine of pi over 6, and look at the cosine of 60 degrees, you'll see that the sine of 30 degrees and the cosine of 60 degrees are the same value because they're cofunctions. Okay? So those cofunctions have the same value for complementary angles. The sine of 20 and the cosine of 50 degrees would be the same. Okay? So the cofunction for the cosine is the sine. The cofunction for the tangent, as you might expect, is the cotangent. Okay, so we can fill in both of those. And then the secant and the cosecant are cofunctions. So if you pick out your 30 degree and your 60 degree and you go down your table, you'll see that the sine of 30 and the cosine of 60 are the same. The tangent of 30 and the cotangent of 60 are the same. Okay? And same thing with secant of 30 and cosecant of 60. Okay? Those complementary angles, their cofunctions have the same values. Okay? That's just one of those neat little perks. Okay? So, tomorrow in class, we'll go over day 5. I'm not sure if that's exactly what it still is going to be. I'm going to take another look at that, so we'll just cross that off. So, right triangle trigonometry, the sine being the ratio of the opposite side over the hypotenuse, the cosine is the adjacent side over the hypotenuse, tangent is the opposite over the adjacent, okay? And we'll do a lot more with that right triangle trigonometry as we move through the chapter, and we'll use those things to be able to find lengths or heights of things that we can't measure directly. So, make sure you go over those notes, and make sure you're ready to hit on those problems when we get to class tomorrow. We'll see you then.